The third law that we study in my class is called Gay-Lussacs Law, and it's named after a scientist who studied gases that dealt with pressure and temperature. I want you to take a look at this goofy cartoon that we see here. On the left side, we see half a man being supported over some kind of canister or container containing a gas, and there's half a candle underneath it. And then if you look to the right, in the center, you have an entire man who's being held at the same level by a whole candle, by one candle as well. On the right hand side you have two people, and there are two candles underneath the gas canister, and it seems to be holding up those two people at the same particular height. So what we have here is we have a difference in the amount of heat that's being applied to each one of these gas canisters, and the internal pressure seems to be compensating for that heat and holding up all three of these people or parts of people at the same height. Taken another way, we could say this. We could say, graphically speaking, as temperature goes up, pressure also goes up. And you can see here on the graph that on the x-axis that we have temperature, and this would be increasing values as you move to the right. And corresponding on the y-axis, you have pressures that are also going up in a directly proportional type of relationship. I want you to take a look at a little visual that I have here. And this is an animation showing a gas canister with helium gas on the inside of it. Now, I have some controls over here on the left hand side, and currently at the lowest possible temperature for this canister at 150 Kelvin, I have a pressure of 6.67 atms. But I can use this little slider bar and I can start increasing the temperature, and we can start to see what happens to the gas as it responds to that increase in temp. So as I move it to the right, I'll just grab the slider and start sliding it. You can see that the velocity of the particles is increasing. And if you look at the pressure number, which is right here, it's also increasing at the same time. So if I keep going right, we keep seeing these internal particles of the gas starting to move faster and faster. And that also means not only are they banging into each other more often, but they're hitting the walls, which is going to be responsible for an increase in temperature. So if I go ahead and I push it all the way to the right at the highest possible temperature for this scenario, 300 K, you can see that the gas particles of helium are moving much, much quicker. As I move back down to the left, watching the graph form up here, how it will decrease in temperature, decrease in pressure as I move the temperature down. You see it slide back down the hill there until I wind up getting right back to the base. So again, and watch the particles at this point, they're moving much, much slower again. So once again, if I move to the right, you can see the graph climbs up and to the right, directly proportional relationship. And as I cool it back down, they go back down again in both pressure and temp, directly proportional. Okay, so what I want to do then is I want to revisit the Gay-Lussacs Law and what it looks like. So the mathematics behind the law are simply this. He experimented and he found that pressure and temperature were directly proportional to one another. He was able to reconfigure that equation for a temperature at two different conditions. At condition 1, or initial conditions, P1 and T1, and then at condition set number 2, which is why again we put those little 1s and 2s behind it. The 2s would stand for the second condition, or the final condition of that particular gas. Okay, so let's look at an example. Someone who has never taken chemistry and learned about the gas laws decides to throw an aerosol can into the campfire to get rid of his or her trash. It's originally at a temp of 23 degrees Celsius and has a pressure of 43.1 psi. After 3 minutes in the fire, the temp of the can and its contents is 288 degrees Celsius. What is the new pressure? Okay, so what I want to do then is I want to go ahead and kind of take apart the scenario and write what each of the variables is going to be. So let me find an appropriate color here. White's going to work against this background. So we have initial temp of T1 and the temp was 23 degrees Celsius. So 23 degrees C. We have a pressure, a P1 at that point of 43.1. There we go, PSI. Our second temp, which is given, it rises up to 288 degrees Celsius, 288 degrees C. And the question is, what is the new pressure? So P2 then is going to be unknown. So just like Boyle's law, just like Charles' law, we have 3 out of the 4 variables, which means we can always solve for the 4th. So before we do that, though, let's come up with a prediction. And what I mean by that is, what do we think is going to happen with the pressure? We started with a atmospheric temperature aerosol can. We threw it in the fire. From the previous graphs that we saw, we can then make a judgment call on what we believe is going to happen. And hopefully, through life experience, you know that if you were to put an aerosol can into a fire, that pressure is going to increase as the temperature goes up. Okay, so let's go ahead and look at the mathematics that back this up. We get a numerical value for an end answer here. So, to solve. Here is our table of known values. It's still here on the screen. And what we're going to need to do then is we're going to need to pop it into the formula. So the formula is P1 over T1 equals P2 over T2. Okay, so our P1 then was 43.1 PSI. And we're going to put that over initial temp 1 of 23 degrees Celsius. Now, if you remember from our previous talks, we are now changing our Celsius temperatures to Kelvin. So we're going to add to our 23 273 to convert from Celsius to Kelvin. So this would be 296 K. Okay, and that's what's going to go down here then for T1, 296 K. Okay, on the other hand, on the other side of our equation, we have P2, which is still unknown, so I'm going to leave it as P2. And our new T2 temperature, we're going to have to go ahead and change it from, again, Celsius to Kelvin. So we have 288 plus 273, and that winds up being 561 Kelvin. So that's going to go down here underneath the division line, 561 K. Okay, so we are currently in the spot where now we have to get the variables isolated, the variable we're interested in, and that happens to be P2. So what we're going to do then is we are going to take our 561 and we want to get rid of it off the right-hand side of this equation. So what we'll do, algebraically speaking, you remember we would probably multiply both sides by 561. You could think of it that way. You can also think of it as dragging it up diagonally through the equal sign to join up with the 43.1 that's currently on the top. So we would then have 43.1 PSI, and I'm going to go ahead and put that in parentheses. It is now joined by the 561K. And that's going to be divided still by the 296K. Okay? And you'll notice that I'm leaving my units in the problem. The reason I do that is because it makes my final answer guaranteed to have the right unit, and here's why. Whenever we have a K over a K, or any other variable over another variable, we know they cross-cancel. They cancel out. So in this case here, my K's get slashed, and all that's left is PSI, which fits because we're looking for, again, for P2. So then we multiply 43.1 times 561, and we're going to divide that by 296. And after the math is all done, you should wind up, and you can check it on your calculator, of 81.68, and the unit is the only one left over, which is PSI. Now, little polishing up of our answer here. If you look in the problem here, we have 3 significant digits for each value, which means we should only have 3 significant digits for our final answer. So I'm just going to tidy up my answer at the end. I'm going to put it in scientific notation as well. So I'm going to keep the 3 most important digits, which is going to be an 8, a 1, and a 7. The reason I chose 7 is because there's an 8 following the 6. I'm going to put my decimal point in here, put my times 10 because this is scientific notation, and it would be 10 to the first power because 8.17 times 10 is 81, and therefore we are just about done. So the question remains, does our final answer match our prediction? We predicted that the PSI would go up. It absolutely did. So here we have 81.68, where our initial pressure was 43.1, so it had about doubled by throwing that can into the fire. And I'm sure we can make the ultimate prediction of what's going to happen to that aerosol can if we leave it in there any longer. Once the structural integrity of the can has been compromised, it's going to be a very massive release of gas at that point when it does go through combustion. So I hope this helps you understand Gay-Lussacs Law a little bit better. Just quick little summary here. Pressure and temperature, they are directly proportional to each other. As one goes up, the other one goes up as well. So good luck studying, and see you next time.